Hey everybody, Trey here. Welcome back to another episode in this Skew-T and Hodograph series. It's been a while since we've done a video in this series, but we're going to get back on the horse, try to finish up this series in the next few videos. If you recall, in our last couple of videos in this series, we started to decipher these SPC and model soundings. We started up here at the top left with the Skew-T portion of the sounding, and then moved on to the Hodograph portion of the sounding over here on the top right. Well, now we're going to move down here to the bottom half of the sounding. Take a look at all this mumbo jumbo down here. There's a bunch of different parameters, bunch of different boxes down here. I'm going to take you through each and every one, tell you what each of them means and why they're important. And I'm going to tell you which ones that I like to use when I'm making a severe weather forecast. Again, there's a bunch of different parameters down here that are derived from the sounding that are listed down here. But not all of them really make a difference when you're making a severe weather forecast. So I'm going to give you all of the meanings and all the importance behind each parameter, each box down here, so that you can make your own decisions on what to use when making a severe weather forecast. But I'm going to tell you which ones that I like to use and focus on when I'm making a forecast myself. So without further ado, let's go ahead and get started here. The first box that we're going to take a look at here is this one on the far left-hand side. This may take a couple of different videos to get through all of these, but this is going to be the portion of the sounding where our thermodynamic parameters are listed. We're going to start here with this topmost portion of this box. It's going to be this one here at the top left, and that is going to be where all of our different parcels and their associated parameters are listed. Now, when I say a bunch of different parcels, what I mean is, if you recall back earlier in the series, way earlier in the series, first couple of videos of the series, we actually made our own sounding. And if you recall, we made a parcel trace on that sounding, and that's represented here on this sounding by the dashed brown line. And what we did for our sounding when we made our own is we went up from the surface temperature and surface dew point. We went up along the dry adiabat from the surface temperature, and then along the mixing ratio line associated with the surface dew point. And wherever those points, those lines met, was our lifted condensation level. And from there we went up along the moist adiabat through the depths of the atmosphere. Now that was using the surface parcel, or SB parcel, our surface-based parcel. And again, what that is going to be, it's going to be listed here, the first of our parcels, and that is going to be our parcel that's lifted using the surface temperature and surface dew point. So the way that we've done it before in this series of making our own parcel traces. And just before we move on, this is going to be where all of our parcels are listed here. And then we have our columns here. Of course, this leftmost column is our type of parcel that's being lifted. The next one is going to be our CAPE, convective available potential energy. Again, you can go back and review these terms that I'm going to talk about here in the previous videos of the series. I'll try to give a brief overview of them here just to kind of jog your memory. CAPE is going to be that positive area between the parcel trace and the environmental temperature profile when the parcel trace is warmer than the environment. So it's going to be that positive buoyancy, that area between the two curves when that's the case. The next column here is convective inhibition, so it's going to be the opposite of CAPE. It's going to be when the parcel is cooler than the environment, and the area between the two curves then is going to be our convective inhibition. Then we have our lifted condensation level. Again, it's that point where that's that lowest theoretical cloud base, that point where the parcel first becomes saturated. So we go up from the surface dew point, surface temperature and surface dew point along the dry adiabat and mixing ratio lines respectively. And the point where those two meet is going to be our lifted condensation level for our surface-based parcel. Then we have lifted index. It's one of those composite indices that we use to decipher instability in the atmosphere. Again, not going to be as accurate, as meaningful as convective available potential energy is, but it is another metric to describe atmospheric stability or instability. Then we have our level of free convection here. It's that point above the LCL. That is the first point above the LCL at which the parcel becomes warmer than the environment. Then we have our equilibrium level. It's that first point above the LFC, the level of free convection, where the parcel becomes cooler than the environment. So those are all listed there. Now back to our surface-based parcel here. So again, that's going to be we're going to lift that parcel using the surface temperature and the surface dew point. So we're going to go up from the surface temperature along the dry adiabat, up from the surface dew point along the mixing ratio line, and then follow the moist adiabat up from the LCL. That's going to be our surface-based parcel. But that's not going to be as accurate because we're only taking into account one single parcel, and not all of our parcels are going to be, located at the surface. So that's not going to be super accurate. Instead, what we like to use, and what I like to use, and what most meteorologists use when they're determining instability in the atmosphere, is going to be our mixed layer parcel, or our ML parcel. And the mixed layer parcel is going to take an average of the surface, it's going to take an average of the temperature and the dew point, basically the characteristics of the parcels in the lowest 100 millibars of the sounding. So in this case, the surface would be somewhere just above 1,000 millibars, so something like 990 millibars. So we'd go up to about 890 millibars, and we'd take an average of the characteristics of the parcels in that layer. And then we would lift our parcel using the average of all those parcels in that layer. So that is going to be a much more realistic depiction of a parcel that's being lifted in the atmosphere, because we're taking an average of the parcels in that lowest 100 millibars of the sounding. For example, let's say we have a lot of moisture, very high moisture content in a very shallow layer here just above the surface, and then we really start to tail off right above that. So pretend our dew point line here looks something like this. So a very shallow moist layer, and then we really start to tail off above that. Well, if we're using just the surface-based parcel, we're going to get an overestimation, a misrepresentation of what the actual parcel is going to experience when it rises in the atmosphere. Of course, we've talked about mixing before in this video series. Mixing is when we mix air from above down below and air from below to above, and we get kind of oftentimes a decrease in the dew points because drier air can get mixed down to the low levels when we have surface heating. Well, that's the same thing when a parcel goes up. If it goes up in an environment like this, our hypothetical environment here, it's going to start mixing some of that dry air into the parcel because our air is so dry just above that very shallow moist layer there near the surface. So if we used our surface-based parcel there for determining instability in this hypothetical situation, we would get a drastic overestimation of the instability in the atmosphere because we're just taking into account the surface-based parcel, which is assuming this environment is going to be the same as we go up in the atmosphere. So we're going to see a very moist environment when in reality we have lots of dry air just above that. But using the mixed layer parcel, we're going to take into account all of this in that lowest 100 millibars. And we're going to get a much more representative value for instability and the other parameters there. So again, mixed layer is going to be one that you're going to want to use when you're determining instability. I'm planning on doing a video on why surface-based CAPE is a lot less favorable to use than mixed layer CAPE when making a forecast in the future. But for now, just know that mixed layer CAPE is much more representative. It's much more representative of the overall environment than the surface-based parcel is. So then we have one that's called the forecast surface parcel. What the forecast surface parcel is it lifts a parcel using the estimated afternoon temperature, so kind of that max temperature that we've talked about before. It's going to be an estimate of the afternoon maximum temperature combined with the mean mixing ratio or dew point in the lowest 100 millibars of the sounding. So it's kind of a combination of the surface-based and the mixed layer parcel. It uses that estimated afternoon maximum temperature. So it's going to be a lot warmer than it is now, given if this was say a 12Z sounding, it would be a lot warmer than it is on the 12Z sounding. So for example, this max T would be 83 degrees Fahrenheit, so it would be somewhere out in here. And then we would average that dew point in the lowest 100 millibars of the sounding, and we get a parcel that would look something roughly like this. And you can see it provides a lot more instability than what we were talking about with our surface-based and mixed layer parcels. So forecast surface is not something that is used that often. I've never used it when making a severe weather forecast, but it is listed on the sounding. And one difference that you'll see from model soundings to the SPC sounding, particularly if you're using College of DuPage, it has the same parcels here, but it lists this parcel as the effective parcel. And I'm not 100% certain that this is the exact same as the forecast surface parcel, but from what the documentation I've read from the investigation that I've done, it is pretty much the same parcel. So if you see EFF there on College of DuPage soundings. I would believe that that's akin to the forecast surface parcel listed on the SPC soundings there. So again, not something that's used very often, the forecast surface parcel, but it is listed on the sounding as well. Then we have the most unstable parcel, or the mu parcel, most unstable. And that is going to be a parcel that we use often for elevated convection. And that's because the way we find the most unstable parcel is we calculate the equivalent potential temperature, or theta E, for each level in the lowest 300 millibars of the sounding. So if you can think of this as about 990, we'd go up to about 690. And in that layer, we're going to calculate the theta E, the equivalent potential temperature for every single layer in that sounding. And if you recall, the theta E, the equivalent potential temperature, the equivalent portion of that means we get all the water out. So we lift the parcel up until there's basically no more water in that. And then potential means that we take it all the way back down along the dry adiabat to 1,000 millibars. And that gives us our theta E. So again, we're calculating the theta E in the lowest 300 millibars of the sounding. And the level at which the theta E is highest in that layer is going to be the level at which we are lifting the parcel from. So we, again, calculate all the theta E's. The level at which it's greatest in that lowest 300 millibars is going to be the level at which we're using for the most unstable parcel. And again, it's going to be most useful for elevated convection, because this parcel, oftentimes the most unstable parcel is not going to be at the surface. You're going to see a lot more, oftentimes, as we've done in our forecast videos previously, you often see that the lapse rates are much steeper in the middle portion of the sounding. Often there can be some more moisture up there as well, so the theta E is oftentimes a lot greater up here aloft than it is near the surface. And as a result, the most unstable parcel is going to be usually elevated away from the surface. So it is used at some times for elevated convection when you have kind of a stable layer near the surface. Oftentimes you will go right to the most unstable cape. But for normal kind of severe weather soundings, for your kind of tornadic events, we're never really going to use the most unstable parcel. We're going to use the mixed layer parcel, and sometimes surface based, but again, surface can be a misrepresentation of the overall environment. So we use mixed layer most often for our using when we're looking for instability. So that's going to be our top box, again, CAPE here. So the brown dashed line here on the SPC sounding is going to be that most unstable parcel. They plot the most unstable parcel. I'm not 100% sure why they plot the most unstable parcel here with this dark brown dashed line, but that is what it is, and it does give a decent sort of first kind of glance at the overall distribution of instability in the profile. But again, mixed layer is going to be a lot more relevant, a lot more accurate when we're making an instability forecast. So if we're comparing the different parcels here in this particular sounding, you'll notice that the surface parcel is actually going to be a lot less unstable, or a lot more stable, than the mixed layer parcel is. And that is often not the case. Almost all of the time, the mixed layer parcel, the mixed layer CAPE, is going to be less than the surface-based CAPE. Again, that's because oftentimes the surface-based parcel has the most kind of, the highest temperature, the highest dew point, when you can have some drier air aloft that may, inhibit that mixed layer CAPE. And that's why, again, mixed layer CAPE is a lot more reasonable to use than surface-based CAPE is. But in this particular example, which is kind of unusual, the surface-based CAPE is a lot less than the mixed layer CAPE. You see 1258 joules per kilogram here, 1860 here for mixed layer. Again, that forecast surface using that afternoon high temperature, which is going to be a lot higher than oftentimes than the surface temperature is, we get a lot more instability here. Again, that's unrealistic. Almost 3,000 joules per kilogram of CAPE, when the mixed layer parcel is showing only about 1860 joules per kilogram. And then that most unstable CAPE, again, is a little bit exaggerated in this case. We're not dealing with elevated convection here, but the most unstable parcel a little bit higher than what the mixed layer CAPE is showing, and that's generally going to be the case as well. Convective inhibition here, using the surface-based parcel, we see a lot more convective inhibition than the mixed layer parcel, almost about negative 100 joules per kilogram of convective inhibition there. That's because if you use your surface-based parcel, we're going to see quite a bit of sin here in the lowest levels of the atmosphere. You can see that the parcel trace there using the surface parcel is going to be to the left of that environmental profile, temperature profile, for a decent chunk of this, at least here in the low levels. And that's why we're seeing quite a bit of inhibition here, whereas if we use the mixed layer parcel, taking an average of that lowest 100 millibars here, very juicy air there in the lowest level, so that may be why we're seeing a little bit more unstable and a little bit less convective inhibition with this mixed layer parcel than the surface-based parcel, which again is quite unusual. Forecast surface, because we're using that max temperature, basically that estimated afternoon temperature is going to be out here, so we're not going to have really any convective inhibition to deal with, and we're going to see a lot fatter CAPE than what is actually observed in the atmosphere there. And then most unstable, again, that's going to be plotted here using that most unstable parcel. You can see it's not quite based at the surface. It's a little bit above the surface here in this example, which again, why we use most unstable most of the time for elevated convection. So one more thing here, you'll notice that the values here of equilibrium level, LFC, LCL are plotted here on the right-hand portion of the Skew-T as we talked about before. But you'll notice that we use different parcels to plot each of these. Now this one, the LCL is plotted here on the Skew-T portion of the sounding using the mixed layer parcel. So in this case would be about 678 meters. Then for the LFC, the equilibrium level, and the mean parcel level, we use the most unstable parcel. Not quite sure why that's the case, why they don't just use one parcel for the entirety for each different variable here, but that's the way it is plotted here on these soundings. Again, the LCL is using the mixed layer parcel, the LFC is using the most unstable parcel, as is the equilibrium level and the mean parcel level there. So just something to note there. And with that, we will move on to the bottom box here, to the middle box here, and take a look at all these different thermodynamic variables in this middle section. Now, the way the SPC sounding lays out this middle section here is a little bit different than how the model lays out the middle section. We're going to see mostly the same parameters. In fact, almost all the parameters are going to be exactly the same. They're just going to be listed in a different order and in a little bit different fashion here on the model soundings and the SPC sounding. So I'm going to go through the SPC sounding parameters first, and then go through at the end and show you how the model sounding differs in this middle section here. So first one we're going to start with is precipitable water. It's this PW right here. And again, that is precipitable water. And what precipitable water is basically the total amount of water available within the lowest 400 millibars of the sounding. So again, in this sounding, about 990 millibars. Go up about 400 millibars from that. We see go up to about 590. It's the total amount of water, essentially condensed water, that exists in this 400 millibar layer, this layer in the lowest 400 millibars of the sounding. It is a good parameter to use for heavy rain scenarios, particularly flash flooding scenarios. I know oftentimes in monsoon season forecasting down in the southwest, we like to look at precipitable water to see how water loaded the storms are going to be. In a severe weather sense, it's not super important. It can tell you how wet the storms are going to be, so to speak. I like to use the distribution of the moisture of the dew point throughout the entire profile a little bit more. It kind of gives us a little bit more holistic view of the moisture content in the atmosphere. But precipitable water is good for kind of giving you for flash flood forecasting in sort of a heavy rain forecast sense. But in a severe weather sense, it's not super important. So now we're going to move on to this K value right here. And we've talked about this in a previous video. This is the K index. It's one of those composite indices that kind of gives us a quick snapshot of the stability or instability of the atmosphere. And just as a quick refresher, the K index is calculated in the following manner. We take the 850 millibar temperature minus the 500 millibar temperature plus the dew point, or TD at 850, minus the difference between the 700 millibar temperature and the 700 millibar dew point. That is the K index, and again, it tells us whether or not deep convection is favored. Values kind of greater than 30 to 40 tend to be associated with deep convection, and the greater the K index, the more likely thunderstorms are. All other things equal. Again, it just gives us a snapshot of the instability in the atmosphere and is not a super reliable metric in the atmosphere. So I don't really use the K index when I'm making a forecast for severe weather. We'll move on now to these two right in here, your MidRH and your LowRH. And these basically stand for the mid-level relative humidity and the low-level relative humidity. So the mid-level relative humidity, or MidRH, is going to be the average of the relative humidity values at 150 millibars and 350 millibars above the surface pressure. So we'll say above surface pressure there, ASP for a quick abbreviation there. So that is going to be your mid-level relative humidity. It's going to be the average of the relative humidity at 150 millibars above the surface and 350 millibars above the surface. And the low-level relative humidity is going to be the same thing. It's going to be the average of the surface relative humidity and the 150 millibar above surface relative humidity. So it's just another kind of moisture metric. It tells us the moisture quality or content in the mid-levels of the atmosphere and the low levels of the atmosphere. I have never used these when making a forecast. They're not really super important. Again, I like to look at the overall distribution of the dew point profile throughout the entire atmosphere to tell me kind of the same things. Because in this particular sounding, you can kind of sense that 150 millibars above the surface is going to be about right in here, and 350 millibars above the surface, somewhere roughly in this level. So if I were to average these two, I know there's a little bit of dry air in this layer, a little bit of a remnant elevated mixed layer, so a little bit of warm dry air in this layer above a very deep moist layer here. So by that I can tell you that we're going to have some conditional instability. The moisture content in the mid-levels it's a little bit drier air there, so we're going to have a little bit of a cap, et cetera, et cetera, et cetera. You can see where I'm going with that. These values here, not super important at all when making a forecast, so I don't use those at all. And again, relative humidity is a relative metric. It depends on the temperature of the air, and it changes with changing air temperature. So unlike a metric like dew point, which does not change with changing air temperature, relative humidity is not really a reliable metric to use for assessing moisture content in the atmosphere. And then we have this one here, this sig severe parameter. This is going to be another one of those composite parameters, and it's going to be your significant severe parameter. So this sig severe parameter is a very simple parameter. It's going to be the mixed layer CAPE times your 0 to 6 kilometer bulk shear. That's it. So it's a very crude estimation of the potential for significant severe weather in a given environment. Again, it's a very simple calculation. Instability times shear, does not have anything to normalize it, anything to standardize it. So it's a pretty useless parameter in my opinion. Its units are going to be meters cubed per seconds cubed, and it comes out as a result of the multiplication between CAPE and shear. But again, it's not really used that often. I've never used it at all. You can tell whether or not you have a severe weather environment just by looking at the sounding, the Skew-T, the hodograph, and get a much more holistic view than just looking at a single composite parameter. So would not use this at all when making a forecast. It gives you a very, very crude snapshot of the severe weather potential in a given environment. But again, you can figure out whether an environment will feature severe weather by looking at a more holistic approach using the Skew-T and the hodograph. So now we're going to talk about 3-CAPE. And 3-CAPE is one of the most important parameters that I like to use when making a severe weather forecast, particularly for tornadic supercell events. And 3-CAPE is going to be your CAPE, your mixed layer CAPE, using that mixed layer parcel in the lowest 3 kilometers of the atmosphere. So your 3-CAPE is basically your 0 to 3 kilometer CAPE. and this is extremely important, is when you have higher values of 3 CAPE, that means the instability in the lowest levels is very, very high. And if you have surface vorticity or lots of spin in the low levels, strong 3 CAPE can help stretch that spin into the vertical and help aid in tornadogenesis in supercells in certain environments. So in this case, we have a decent amount of 3 CAPE, 71 joules per kilogram. Anything above 50 joules per kilogram is usually what I like to use as a lower limit for 3 CAPE. Anything above 50 is adequate for an increased potential for tornadic supercells. And the higher you get, the highest amounts I've seen are well into the 200s joules per kilogram of 3 CAPE. Those are your kind of higher end events, very favorable for tornadogenesis when you have supercells in a high near surface vorticity environment. So again, what it does, high 3 CAPE, high instability in the low levels. If there's lots of spin in the low levels, and you can estimate that from the hodograph, we have lots of curvature here in the low levels of this hodograph, so lots of vorticity, storm relative helicity there in the lowest levels of this hodograph. If you have strong instability in the lowest level, strong 3 CAPE, that spin can be easily stretched into the vertical and help in the tornadogenesis process. This is particularly important for cold core tornado events. And cold core tornado events are different from normal troughs. And this is kind of beyond the scope of this video, but cold core events, if you have your normal trough like there, it's an open wave. But if you have a cold core event, you have a contour at 500 millibars that is closed off, very cold air at the center of that trough, that can actually help aid in tornadogenesis and produce supercells because of the very strong instability near the core of that cold core upper level trough. When maybe the low level shear is displaced out this way, you can actually get tornado events near the center of these cold core 500 millibar systems because the instability, particularly the low level instability, 0 to 3 kilometer CAPE, is so high that it's very much thermodynamically driven, tornadogenesis is, versus more kinematically driven in your more typical sort of 500 millibar trough open wave sort of events. But again, 3 CAPE, very, very important parameter that I like to use. Now, it cannot be used on its own. Just because we have, say, if you have an event where a sounding that says, oh yeah, we have 200 joules per kilogram of 3 CAPE, well, that means nothing without spin near the surface, lots of low-level vorticity or helicity. Just because you have high 3 CAPE does not mean that you will have just an increased chance for tornadoes just because you have high 0 to 3 kilometer CAPE. Now, this is a perfect example of that. This is an example model sounding here. 0 to 3 kilometer CAPE of 161. That is super high. But look at the hodograph. Very, very meager low-level shear. 28 knots of 0 to 1, 28 meters squared per second squared, of 0 to 1 kilometer storm relative helicity. So just because you have high low-level instability does not mean that you will have an increased chance for tornadogenesis in supercells in this environment. You need to have that spin near the surface, that helicity, vorticity near the surface, along with that high 3 CAPE to have an increased chance for tornadogenesis in supercells. All right, so 3 CAPE, very, very important. We'll move on now to DCAPE. And DCAPE stands for downdraft CAPE. And DCAPE, not super important in your typical sort of severe weather sense when we're forecasting for tornadic supercells, because as we know, downdrafts can undercut the rotating updrafts of supercells and sort of negate the tornado threat in storms. But it is important when we're forecasting, say, for monsoon storms, and you can take a look at the DCAPE when you're forecasting for severe weather to see if maybe we're going to see more of an outflow dominant storm mode. Now, downdraft CAPE, how it's calculated is we basically follow the moist adiabat down to the ground from the minimum theta E value in the lowest 400 millibars of the sounding. So we calculate the theta E for all these levels here in the lowest 400 millibars of the Skew-T. And that minimum theta E value, from that level, we would follow the moist adiabat back down to the surface. So it is basically the positive area between that sort of trace there and the environmental temperature profile. We would just calculate the positive buoyancy in that area. And that would be your downdraft CAPE, or DCAPE. Now, generally, DCAPE values greater than 1,000 joules per kilogram are associated with environments that have increasing potential for strong downdraft winds in storms in that environment, or damaging outflow gusts, so to speak. So oftentimes when you're forecasting for the Arizona monsoon or something like that, you'll see downdraft DCAPE values of 12, 13, 14, 1,500 joules per kilogram of CAPE. That's because outflow is usually favored in those storms. You get very high DCAPE values, very strong damaging downburst and outflow winds in high DCAPE environments. So again, for tornadic, I don't use it too often. I use it a little bit when I'm forecasting for the monsoon. Sometimes for severe weather events typical severe weather events out in the plains, you can take a look at DCAPE to see if maybe we have a more outflow dominant storm mode. Again, you can kind of decipher that based on your parcels, how high the LCL is, how much dry air aloft there is. But DCAPE is a decent snapshot for the outflow potential for storms in a given environment. All right, similar, related to DCAPE is your down T, and this stands for your downrush temperature. And your down T is basically the temperature at the ground associated with the DCAPE parcel. So we take that DCAPE parcel, and it's going to be the temperature at the ground, the surface temperature for that parcel. It basically is an estimate of the temperature, the surface temperature within the center of a saturated downdraft. So imagine a water-loaded downdraft microburst full of precipitation. The temperature in the center of that downdraft, saturated with precipitation, that's going to be your downrush temperature, or down T. I've never used it at all. It is associated with DCAPE. It just basically tells you, it can tell you, how strong a downdraft is, how intense a downdraft is, how cold that air is at the center of a downdraft. Not super important in severe weather forecasting. We now have this mean W here, which is going to be our mean mixing ratio. We've talked about W before, standing for mixing ratio. And again, the mixing ratio is that ratio of dry air to saturated air in a parcel. And the mean mixing ratio is going to be that mean mixing ratio in the lowest 100 millibars above ground level. So it gives you a snapshot of how deep the moist layer is, how the moisture quality within the lowest 100 millibars of an environment is. Don't really use it a whole lot. It can be useful, but again, I think you can just see from the distribution of moisture within the Skew-T itself how deep that moist layer is, what the quality of that moisture is in that moist layer. Not super important here, but it can be useful if you're looking at just kind of a snapshot for the moisture quality in the lowest portion of the Skew-T. So we're going to stop here for this video. We've gone on long enough, I think, in this video. We're going to pick up next time with these remaining few parameters of this middle section, then we'll take a look at the bottom section here to close out the next video. But I think we've done enough for today. So thanks for watching, and we will see you in the next video.